Hello everyone, can you hear me?
Yes, ma'am.
So, in we have had only one lecture. So in that lecture, we saw some example of how computing can simplify our life. So why computer intensive methods are useful. Now today I will start with introduction to Bayesian inference. Why Bayesian inference? Because this is part of our first unit. So in first unit we have some algorithms which are related to Bayesian, and as we discussed last time, many of you are not familiar with the ideas of Bayesian inference. So today we'll have some introduction to Bayesian inference, and then we can further learn the actual algorithms that are in the syllabus. So how do you define probability? I mean, when you were in BSc, you defined the concept of probability. So how did we define this? Yes.
Uh, Number of events in that number of outcome in that event upon total number of events.
Okay, number of outcomes favorable to that event upon total number of events. Okay. Any other definitions that come to mind? So one definition he told is number of outcomes favorable to an event, favorable to that particular event whose probability we are finding out. So I'm writing favorable to the event upon total number of outcomes in the sample space. Do we have any assumption under which this definition holds?
All outcomes are equally likely.
Correct. We have to assume that all outcomes are equally likely, then only this will hold true. Correct. So this is true only when you assume equally likely outcomes. Okay. What about others? Any other definitions that come to mind, especially when we don't have equally likely outcomes? I give you a coin and I tell you I don't know whether the coin is biased or unbiased. How are you going to decide what is probability of head?
Limit and n tends to infinity
Correct.
of m upon n.
So what is it called as? Limit of probability is defined as limit of what? What is that quantity called as? Whose limit you are taking? Limit as n tends to infinity of what?
M upon n, where m is the number of favorable outcomes.
Correct. So what is it called as? Number of heads. Let's be precise. Number of heads upon total number of tosses. What is that quantity called as?
Relative frequency.
Correct. Relative frequency. So, in statistics, there are two schools of thought or two schools of methodologies. One of them is what we have been learning since BSc first year. So that is known as frequentist approach, okay, or the classical approach. So frequentist, or it is also known as classical approach because of course it is quite old. And there is another school of thought which is comparatively new, so it is known as Bayesian methodologies. Okay, so in classical approach, generally we think of probability as limit of relative frequency. Now that is for some people that becomes a problem. Okay, for example, if I want to say that what is the what is the probability that I am going to drink coffee after this lecture today. Now when you say some probability is to be computed as limit of relative frequency, you need to repeat that event, right? In the case of coin, you said okay, you will toss the coin maybe 100 times, 1000 times, and every time you will record whether it was heads or tails, and then you will take limit. But now when I say that today after this particular lecture on 9th March, what is the probability that I would drink coffee? Now you cannot really have repetitions of this event because you cannot have this day occur multiple times, or you cannot have too many versions of me, and then you can see how many versions drink coffee and how many versions don't drink coffee. You can't do that, correct? So no repetition is possible here, but still ideally normally we would like to assign probability statement to it. So that creates trouble to some people. So they say that in the frequentist or classical approaches, you cannot really assign probability to events which are non-repeatable. Okay, which are not repeatable. So that's why they say that in those cases Bayesian should be preferred. Okay, so this first consideration is definition of probability as limit of relative frequency. And as I said, that causes issues when you have events that cannot be repeated. So how do you define probability for them? That becomes a problem. That cannot be repeated. Whereas in Bayesian, this is slightly more subjective approach. So if I have some thought process, so if I feel that okay, the chances of me drinking a coffee after this lecture are say 50%, then I can put it in that way itself. I don't have to define it in terms of relative frequency or repetitions. So this subjective thought process can actually be converted into probabilistic statements. Which makes such statements more meaningful. Okay, so in this way you can assign probability to such events which cannot be repeated. Okay, that is one major difference between frequentist and Bayesian approach. Another major difference which is more obvious, this first difference was not that obvious I think, but the second difference is quite obvious. When you talk about any statistical distributions, what is meant by a parameter? What is a parameter? What is a parameter? Am I connected?
A constant value of distribution.
Sorry, I could not hear you. There's some noise. Estimation was the last word, did you say?
A constant from a distribution.
A constant from a distribution. Okay. I just heard the shun part. Okay. A constant from a distribution. Okay. What about others? Do you agree with that statement? Parameter is some sort of constant which governs the probabilities in which we are interested. Is it correct? So parameter, and is it known or unknown?
Most of the times it is unknown.
Okay, so generally an unknown constant, because that's why you do estimation and that's why people have developed statistical theory. Okay, so it is an unknown constant. Okay, and when I say it is constant, what I mean is it's a fixed constant, right? So it's a fixed constant and it does not have any probability distribution associated with it. What do I mean by this? this actually creates trouble in interpretations, and that's why people sometimes favor the Bayesian approach more. See, we have all studied 95% confidence interval, correct? So suppose you have a sample x1, x2, xn coming from normal mu sigma square, then you define mu hat as x bar. Okay, I mean univariate setup. Okay, so we define mu hat as x bar, and then we have let us assume that sigma is known, or even if even if you feel it's unknown, still we can do something about it. So okay, I don't know what this is. Fine. So then you say that 95% confidence interval for mu can be given as mu hat minus 1.96 sigma hat by root 10 and mu hat plus 1.96 sigma hat by root 10. Does this sound familiar? Hello?
Yes, sir.
Okay. So what is the meaning of this? Means what do you mean when you say that this is 95% confidence interval for mu? I feel like I have talked about this in our class. I don't know, multivariate maybe, data mining ideally it shouldn't come up. So what is the meaning of this, that this is a 95% confidence interval for mu? What is the meaning of this statement?
That there is a 95% probability that our population mean lies between this given interval.
Okay, so can I write that suppose this is my I, this interval I call it as set I. So what you are saying is probability that mu belongs to I is 0.95. Is that what you are saying?
Yes, sir.
What about others? Do you agree? Now this is where trouble starts for many people. Just hardly a minute before I was saying that mu is a fixed constant. It is not a random variable. So there is no probability distribution associated with mu. And now I am talking about probability of mu belonging to some interval, and I am saying that probability is 0.95. Ideally, if mu is not random, then this mu is going to be either inside this interval or outside this interval, because mu is a single fixed value. There are not like 100 possible values of mu and then you have different probabilities associated with those values. That's not the case. Mu is a single fixed value. So that value is either inside this interval or outside this interval. So it's 0-1 business. So what is the meaning of this statement then? What is the meaning of this statement then? Because we have been computing 95% confidence interval since you can remember, right?
If we carry out an experiment 100 times, then 95% of 95 times our population parameter will lie in the interval. Out of those 100 intervals.
100 intervals, correct? So what is random here is the interval. So if I repeat this experiment 100 times, so if I somehow have such samples from 100 different people, then I'll get I1, I2, I100 as my 100 intervals, and out of these 100 intervals, roughly 95 intervals are supposed to contain that constant mu that I have, correct? So here what is random is the interval, and the parameter itself is not random. But when we say it's a 95% confidence interval for mu, most of the people think of this as this mu being in this particular interval 95% of the times. So this interpretation makes many people uncomfortable, and Bayesian approach actually has a solution for that. So Bayesian approach assumes that parameters are of course unknown, they are of course constant, but in Bayesian approach, parameters can have their own probability distributions. Okay, can means in fact they have. Okay. Okay, so in Bayesian approach, what we say is this parameter itself has its own probability distribution associated with it. Okay. As a result, you can make such statements that parameter belonging to this interval has this much chances. Okay. So parameter is also a random variable, that is major difference between Bayesian and the frequentist approach. Okay. So of course when I start saying that parameter is random, I need to have special terminologies for it. Okay. That's where we have the concept of prior and posterior distribution. Okay. So normally when we say we have some parameter, we say it's a constant. So in Bayesian philosophy, we will say that suppose my mu itself has some probability distribution f, which would be called as prior distribution. Okay, so the probability distribution of parameter would be called as prior distribution, and then I'll have some data x1, x2, xn, which comes from some g where mu is a parameter, and now on the basis of this data I might update my knowledge about this. Okay, so normally what we do in the classical setup is once you get x1, x2, xn, you use that x1, x2, xn to get mu hat. Correct. Now here what you would do is, instead of simply relying on data, you will use this also. Okay, the prior distribution also. So what does prior distribution indicate, or what does prior distribution tell you? Prior distribution actually tells you something about the process which is already known to the domain experts. Okay, so the domain experts may have their own knowledge about the process which could be used here. Okay, so we'll see two examples of Bayesian in practice. By the way, first obvious question that should come to your mind, why the name Bayesian? Does it have something to do with the Bayes theorem? Yes, it definitely has something to do with the Bayes theorem. So what does it have? So as I said, you have some prior distribution for the parameter, then you have data, and then we try to compute what is known as posterior distribution. So what is a posterior distribution? Posterior distribution is basically you try to predict something about the parameter on the basis of data as well as the prior distribution. So you try to predict distribution of your unknown parameter mu or theta on the basis of x1, x2, xn, and of course the prior distribution. So using your usual conditional probability, what can we say about this? This would become joint upon marginal. Conditional probability is joint probability upon marginal probability. Correct? So joint means what here and marginal means what? So joint would be what? Can I say something like this? And then what would be marginal? Does this look familiar?
The likelihood distribution.
Let me start with the example. Fine. And we'll come back to this. So, doctors know that in general chances of fraternal twins and identical twins. Okay, so what are identical twins and what are fraternal twins? Does everyone know? What are identical twins and what are fraternal twins? Does everyone know? So identical twins are basically twins which have exactly same they are conceived from the same egg. Okay, so they share the exact copy of their DNA, whereas fraternal twins are those which are actually not they are like siblings, so they don't share their entire DNA. Okay, so identical twins are exact copies of each other, and of course that's why identical twins have to be of the same sex. They can't be like brother and sister, either two brothers or two sisters. Okay, so doctors know from their experience over past many years that in general, if someone is going to have twins, then the chances of having identical twins are 1 by 3 and chances of having fraternal twins are 2 by 3. So given that you are already knowing that there are going to be twins, chances of it being identical twins are 1 by 3 and chances of it being fraternal twins are 2 by 3. Okay, now some couple visits the doctor, and this is not the story that happens in India. So they know that okay, they are going to have twins. That of course you will know in India also. They tell you if you are going to have twins, but here we don't reveal the sex of the child before birth, right? In India it is banned, but in many countries you can know the sex of your child before birth. So suppose this couple knows that they are going to have twins and that the twins are of the same sex. Okay, so either two girls or two boys. For our calculation, whether it's a girl or boy doesn't matter. What matters is both have the same sex. Then now with this knowledge, is there the chances of their children being identical or fraternal, do they change or do they remain same with this knowledge? Okay, so this is what is known as prior distribution. Okay, so doctors have this prior knowledge of, so let us say that theta be the probability that a given pair of twins is identical. Okay, so we know that prior distribution is this. Now the couple knows that they are going to have children of same sex. Then do their chances of having an identical or fraternal twin, are they different than 1 by 3, 2 by 3? How would you do these calculations? So let me go to the usual bivariate conditional probabilities that we used to do in BSc. So here we have say different sex and same sex, and here we have identical twins and fraternal twins. Okay, identical twins cannot be of different sex, so this event has probability 0. Okay, probability of intersection of these two things, so identical twins being of different sex, is 0. Now we have only 3 cells to be filled. We already know that identical is, this probability is 1 by 3, and fraternal, this probability is 2 by 3. Okay, so of course, because we know, you all know that marginal probabilities are row sums and column sums, etc. So total probability has to be 1, which is already there. Okay, so this is 1, no doubt about that. This is 0, so this has to be 1 by 3. Now the question remains of this 2 by 3. In fraternal twins, what are the chances of both being of the same sex and both being of the different sex? So there are 4 possibilities: boy girl, girl boy, girl girl, and boy boy, and all are equally likely. We'll assume that in general the sex ratios are same, all are equally likely. So this has probability half, this has probability half, correct? So half of this 2 by 3. Are you following what is happening here? Hello?
Yes, ma'am.
Yeah. So half of this would mean this is 1 by 3, this is 1 by 3. Okay. Now, this couple knows that they are going to have children of same sex. That is already known to them. So conditioned on this fact that they are going to have children of same sex, what would be the distribution of the twins being identical or fraternal? So how do I compute that? Probability of twins being identical given that they are of same sex is same as joint probability of identical and same sex, correct, upon marginal probability of same sex. Is it correct? This you know from your BSc conditional probability. I am not writing anything new. Okay. And what is the joint probability of identical and same sex? So this entry. So this is 1 by 3 upon probability of same sex. So marginal distribution of that will be this 1 by 3 plus this 1 by 3. So that is 2 by 3. So this is 1 by 3 upon 2 by 3. So this is half. So probability of identical twin given that they are of same sex is half, whereas normally this on the basis of no data that is the prior probability was 1 by 3. So in the presence of this data that the twins are of same sex, the probabilities have changed. The distribution of identical and fraternal twins has changed. So this is exactly what Bayesian thinking philosophy is. You have some prior assumptions, you have some prior probability distribution coming from your domain knowledge or prior knowledge. However, in the light of current data, in the light of new data, you can use that distribution, prior distribution, in combination with current data to get an updated distribution, which would be known as posterior distribution. And as you can see, how did I compute this probability of same sex? It was addition of these two cells. So basically, this I could write in a slightly different manner. Okay, this same thing I could write in a slightly identifiable form. Probability of identical twin given same sex could be written as probability of this joint probability I could write as another side conditional probability, correct. Joint I could write as this conditional into this marginal divided by probability of same sex given identical into identical plus probability of same sex given fraternal into fraternal. Are you following? Do you agree with me that this probability is same as this sum? Law of total probability, partitioning this event into
Yes,
possibilities, and this is exactly what your Bayes theorem tells, correct. This is exactly Bayes theorem. You invert the conditional probabilities, right? A given bi, you write as bi given a into something, and then you add the similar thing in the denominator. That's why the name Bayes theorem. Okay, you have prior probabilities, you have the data with you, and you combine your knowledge from the prior probabilities and the data to get posterior distribution. That is what Bayesian methodology tells us to do. Okay, so today we'll stop here. In the next lecture we'll have one more example of how Bayesian computations work. So today I tried to give you a brief about just the Bayesian philosophy. So that's why we took an example which could be worked out by hand. So in the next lecture, we'll take an example which needs computer for computing the probabilities, and then we will proceed with the next step. Okay. So meanwhile, try to remember these terms: prior distribution, posterior distribution, and they are related to each other via Bayes theorem. Hence the name Bayesian philosophy, Bayesian inference. Basically, it's a method of inference because you are trying to estimate the parameters, so it's method of inference. And the key difference between Bayesian and the classical or the frequentist approach is that in Bayesian theory, we assume the parameters to have their own probability distribution, which is called as prior distribution, and hence making probability statements with them is quite easy. Okay, so let me stop here. Thank you.